Okay, we're going to do a small recap of how we name coordination compounds. This will be like just a little, a recording of some of the examples that we're going to cover in class, but at least we'll have them here as a reference point once class is over. So for starters, just get my little pointer. When we're talking about coordination compounds, this is an example of what we're looking at. All right, so now you're seeing something that is sketched out. It's not in formula form, but what you're looking at is in the brackets here, this is going to be what's called a complex ion, okay? A complex ion is going to be any type of central transition metal that has ligands attached to it, okay? And when the ligands attach, the complex ion generally, still has a charge on it. That's why it's called an ion. Complex ions can have an overall positive charge or negative charge, right? If the complex ion has a positive charge, you can consider it a complex cation. And if it's got a negative charge, it'll be a complex anion. And it's going to want to form compounds like anything that has a charge, right? So in this example, our complex ion has a positive 3 charge, and so it's going to combine with 3 counter ions, which are just, all that means is that it's an ion with the opposite charge, okay? So it's going to combine with 3 chloride ions to form the overall coordination compound, all right? And so if we were thinking of like how to write this out in formula form, we would use brackets to close in our complex ion. So we've got a cobalt, and these are NH3 ligands that are attached, and there are 6 of them. Okay, so this represents our complex ion, and then we're going to have 3 chlorides attached. All right, so let me just stop sharing the presentation real quick to make sure that everyone sees. That's our middle cobalt. These are our 6 NH3 ligands, and then we have the 3 chlorides attached. This part here is our complex cation. And then this is going to represent the counter ions. And in this case, they're simple anions. They don't have to be simple anions, but in this case, they are. And we're calling it a simple anion because it's just chloride ions. It's not another complex ion. All right. Now, overall, we're going to do a recap of naming coordination compounds in this little video, but I just want to go over some of the wording and vocabulary so that we're on the same page with some of this stuff. It's hard to jump right in if we're not using the same terminology, okay? So complex ions are going to be those ions that we see bracketed off that have the central metal that are going to be bound to ligands, all right? And this term ligand, we're going to use it for, it could be a neutral molecule or it can be an ion, but that species is going to act as a Lewis base, all right, with that central metal kind of acting as the Lewis acid. And they're going to form a coordinate covalent bond, which you'll see a little bit more about in class. That's not super important for what we're talking about right here. When we call something a coordination compound, we're talking about the overall neutral compound that gets made when a complex ion combines with another counter ion, whether it's a simple counter ion or a complex counter ion. But the coordination compound should be neutral. Okay, so complex ions will have a charge, but coordination compounds are going to be neutral, like all compounds are neutral. All right, so these ligands, there's different types of ligands, different classes of ligands. For naming purposes, you do have to be able to recognize the ligands and then give them their appropriate ligand name. So like water isn't going to just be called water in a complex in ion or in a coordination compound. Ammonia is not going to just be called ammonia. All right, but we'll get to that little list of the name changes in a second. Before we get there, I just want to go over some of the important things you want to look at when you're looking at ligands. We have a kind of a shortened list of what they are, of what our possibilities are anyway. And what you're going to notice with ligands is that different ligands have different electrons that they use to attach to the central metal, okay? Not every lone pair of electrons can be used to attach to the central metal. So like you see in chloride, how it's got 8 electrons around it, but it's not like the chloride ion could form like 4 different coordinate covalent bonds with a central metal ion, right? They're just, the lone pairs are too close together for that. So what you're going to see in a lot of these smaller ligands is that only one of the lone pairs that are part of that ligand are going to be used to attach to the central metal. And if your ligand only has one pair of electrons that can form a bond with your central metal, that ligand is called a monodentate ligand, right? That term dentate, you can think about it like teeth. So the ligand is actually going to like bite into the central metal. And so if something is monodentate, it's only going to bite in that central metal at one point, okay, using one pair of electrons. The other possibilities are polydentate ligands. These are going to be ligands that are a little bit bigger. And so there's going to be more space between the lone pairs of electrons that are around the atoms in the ligand. And so they're going to be able to bite into the central metal at more than one point. Okay. Polydentate is the term that we're going to use to generally represent any ligand that can make more than one attachment with the central metal. But if you want to be a little bit more specific, we have bidentate ligands, which can form 2 attachments. And we have hexadentate ligands, which are going to form 6 attachments. All right, that's really the only variation that we're looking at here. And specifically for you, and you have to know which ligands are bidentate and which are hexadentate. The oxalate ion, which is going to be shortened to OX, is a bidentate ligand. And the ethylene diamine ligand, which is shortened as a lowercase en, is a bidentate ligand. So both of these have 2 attachment points. The ethylene diamine tetraacetate ion is your only hexadentate ligand. This is going to have 6 attachment points. Okay, it's a pretty big ion. All of these lone pairs that are circled here are spread out enough that they can each form their own coordination covalent bond with the central metal. Okay. So those are our ligands. So starting this naming process, actually, before we go through the steps, I am going to skip a little bit ahead so we can look at these tables, and then we'll go back and we'll look at the steps. So your ligands are going to have slightly different names when they're part of the complex ion, okay? So you'll see that your common anions, bromide ion, chloride ion, hydroxide ion, cyanide ion, like these are all things that we know. Maybe not the oxalate ion and the ethylene diamine tetraacetate ion. These are kind of new, but the rest of these we've seen before. And you're going to see that the ending of the ion name is going to change when we're considering it as a ligand in a complex ion. So when you have the bromide ion behaving as a ligand, the name of the ion is going to become bromo. Okay, it's going to be bromo when it's behaving like a ligand. For neutral molecules like water, ammonia, things that are, again, very familiar to us, when we have a water molecule acting as a ligand, we're going to call that ligand aqua. When we have ammonia acting as a ligand, we're going to call it amine. Okay, pointing this out here because these are names that you do have to know. All right. So now let's go back and let's talk through these steps. So when you have a complex ion or a coordination compound, the first step that you're going to take, and you have these notes available in your chapter 26 slides, so you can follow along if I switch back and forth between the PowerPoint and the board here, just for you to realize. But I think that we'll go through the steps. I'll kind of talk through the steps as we name this complex ion and coordination compound for an example. Okay. The first thing that you want to do when you are going through the naming process is look at your compound and decide whether the complex ion that you're working with is going to be an anion or a cation. Okay. You can tell this by the position of the brackets. Okay. If the first thing in your coordination compound is a bracket, that means that your complex ion is going to be a cation, because positive charges always come first when we're listing out formulas. All right, and that means that what follows is going to be a simple anion in this case. And now your first step when you're going through the naming process is to look inside of the brackets, identify the ligands, and give them their names. Okay, so in this case, we have 6 NH3 ligands. It's only one type of ligand. So we can write that down. We have amine ligands. Right? If we had more than one ligand, we would give them all their names. The second step is going to be to take your ligands and then list them in alphabetical order. Okay? When you're writing out the full name, the names of the ligands are going to come before the metal name in your brackets. And you want your ligands to be in alphabetical order. They have to be in alphabetical order before we do the next step, which is to put a prefix in front of them telling us how many of the ligands there are. So you do not want to alphabetize using the prefixes. You want to alphabetize before the prefixes. All right, and we'll see that in some of the other examples. This one, we only have one type of ligand, so we're not alphabetizing. After everything is alphabetized, you're going to use a prefix before the ligand name to tell us how many ligands there are. The type of prefix that we use depends on the type of ligand that we're working with. Okay. So again, this is why you have to know whether you're working with, like you have to know the names of the different ligands, because you have to be able to tell when you're using, in this case, one type of prefix versus another. Any ligand that has a prefix as part of its name has to use a separate set of prefixes, right? So that sounds confusing when I first say it, but let's list out the common prefixes and then maybe it'll make more sense. So if we have 2 ligands, the prefix is going to be di. If we have 3 ligands, it's going to be tri. These should all seem very familiar. If we have 4 ligands, our prefix is going to be tetra. 5 is going to be penta. and 6 is going to be hexa. Okay, so like when we look at our compound here, we have 6 NH3s, and so we would put a hexa in front of our amine. Okay. Now the other statement that I made, where I said we have a separate set of prefixes for the ligands that have these prefixes as part of their names, say that we didn't have amine. Say that we were using that EN ligand, right? When I write out the name of this ligand, it's ethylene diamine. So you see how this name has a prefix already in it? That means that if my compound has 2 of these or 3 of these, I can't use one of these prefixes to indicate how many ethylene diamines I have. I have to use a separate set of prefixes for something like ethylene diamine. All right. So for this very special case, and for the ligands that we're working with, these prefixes are only going to apply really to ethylene diamine, because the only ligands that we work with that meet this criteria are ethylene diamine and ethylene diamine tetraacetate ion. But we're not going to have more than one of those because they're so big. So these prefixes are really going to be used in our examples for ethylene diamine, but just know that the reason why we're using it here is because there's already a prefix in this name. Okay, so if we have 2 ethylene diamines, the prefix that we're going to use is bis. 3 is going to be tris for any Witcher fans. And then 4 is going to be tetrakis. All right, so like if I had a cobalt with 3 ethylene diamines attached, the way that I would write out the prefix, I would say tris. And then because it's one of these special ligands, I'm going to put a parentheses here. So tris ethylene diamine. All right. But again, that's not the example we're working with just a second. So let's go back to our hexaamine. Once we have our prefixes added to our ligands, then we're going to work on naming our metal. Okay. Naming our metal, first step here, we have to figure out what the oxidation state of that metal is. Okay. So this goes back to our assigning our oxidation number rules that we just were going over in chapter 20. So you want to look at this compound, and you can actually use the charges of the different molecules and ions to help you out with this. We know that when neutral molecules are added together, their oxidations will equal 0. We know that when you're looking at monoatomic ions, their oxidations are going to add up to whatever the charge is on that ion. So you can kind of use that information to help you figure out what the oxidation of your metal is going to be. So you know that whatever the oxidation of the individual nitrogen and hydrogens are, when you add them together, overall the NH3 is going to add up to 0 because ammonia is neutral and it has no charge. So the oxidation number of all of this added together is going to be 0. The oxidation of each chloride ion is going to be -1, right? So the total here is going to be -3. And if I'm looking at a compound, which is overall neutral, that means that the oxidation number on my cobalt is going to have to be a +3 to balance out the -3 here. Okay. So now I'm going to take that oxidation number, all right, and I'm going to use it as part of the name, right? So when you are working with a complex cation, which is what we're working with here, we don't have to change the name of our metal, of the metal itself. We're just going to write the name of the metal and then write the oxidation state after it, but with Roman numerals. Okay. I think I said that clear enough. We're going to write the name of the metal, and then we're going to write the oxidation state after it in parentheses in Roman numerals. So here we have our hexaamine, and now we're going to put cobalt, parentheses, 3. Okay. So this, you're all going to write as like one word, no spaces. And this represents everything that is in these parentheses or in these brackets, okay? Now, to finish this name off, you're going to look at your other ion, your counter ion here, and you name it just like you would name chloride in a regular compound. Like if it was NaCl, this would be sodium chloride, right? Sodium space chloride. If it was, maybe a better example is like CaCl2, right? I've got calcium space chloride. Because I'm working with an ionic compound, I don't have to include any prefixes to tell me how many chlorides I have. I should be able to figure that out based on the charge of what's attached to it. And that same thing is true here. I know that cobalt has a +3 charge, so I know how many chlorides I would need in order to balance that charge out. So my final step is going to be to name my anion, and in this case, it's just the chloride ion. Okay, so that would be my final name. Let's look at the next example. All right, so the next example, and again, this is gonna be the ones from your slides that I'm just talking through here. We have Cr H2O 5 Cl Cl2. Okay, so what can be confusing here when you're just looking at this right off the bat, there's chlorine inside the bracket, there's chlorine outside the bracket, right? But what you want to remember is that anything that's inside of those brackets is separate from whatever's outside. Anything inside of the bracket is going to be part of your complex ion. Okay, so in this case, all of this is part of your complex ion. And because the bracketed material comes first in your formula, you know that it's going to be a complex cation and it's going to have a positive charge. And this is going to be our simple anion. And you can even name it now. You know that it's just chloride. So when we're finishing up our name, this is going to be the ending part of our name. All right, but now we're going to work through those same steps that we already talked about to name our complex cation, starting with looking at the ligands and giving them their names. Okay, so I've got H2O and I've got Cl. I know that my H2O ligand is going to be aqua, And I know that my Cl ligand is actually Cl minus, the chloride ion, and it's going to be chloro. Okay, so now when I'm putting the name together, I want to make sure that I list the aqua before the chloro because I want to put these in alphabetical order. All right. But before I can write out the name, I have to make sure that I include my prefixes. I have 5 waters. So my prefix that goes in front of the aqua will be penta. I don't need a prefix in front of the chloro because I only have one of them. All right, so now my ligands are all named. And now I have to look at my chromium and I have to figure out what its oxidation state is. Okay, so again, we're going to do this just like before. We know that I have 2 chlorides here. Each is going to be a -1. I have a chloride here. That's going to be a -1. I have an H2O ligand here, right? H2O is neutral. So I know that all of this is going to add up to 0. And if my overall compound has to add up to 0, and I have 3 -1s, my chromium has to be a +3 to counteract that. Okay, so penta, aqua, chloro. And now I'm going to name my metal chromium parentheses 3. That names my complex cation. And then space chloride. All right. Now let's look at an example where we have a complex anion. So we can talk about a slight difference that happens when we name our metal. Okay. So we're going to look at the example K3 FeCN6. All right. And when we go and do our first step here, our first step should be to look at our compound, our coordination compound. And in this case, we see that the parentheses are not first. And that means that potassium is our cation. And everything that comes after the potassium is going to represent our complex anion. Okay? When you're naming something, the cation always gets named first, and the anion always gets named second. So we know that the beginning of our name is going to be the potassium. We'll write it down later, but we would know that. Like, our name is going to start with the potassium, and it's going to be followed with our complex anion name. But let's work on figuring out what the name of that complex anion is. So really our steps at the beginning are still very similar. We figured out that this is an anion, but before we do anything else, we have to name the ligands that are here. Okay, there's only one type of ligand, and it's going to be the Cn- ligand, which is cyanide, which we know from our list of names has cyano as its name when it's acting as a ligand. And there are going to be 6 of them. So we're going to call this hexacyano. Okay. Now for our metal, that's part of our complex ion specifically, we have to find its oxidation state. All right. So erase this part so that we can kind of do what we were doing before. We're just going to be looking, we're just looking at the oxidation state of a different metal in this case, right? A different part of our compound. Again, we know that overall our coordination compound is going to be neutral. And now we can use the information we know about potassium and about cyanide to figure out the oxidation of the iron. We know that potassium is in group 1 of our periodic table. So every potassium is going to have a +1 charge and a +1 oxidation state. There are 3 of them. So my total here is going to be +3 from the potassium. I've got 6 cyanides. Each cyanide has a charge of -1, right? That's 6 -1s. That's a total of -6. And when I add all of the oxidations of the potassium, the cyanide, and the iron together, they have to add up to 0. And that means the oxidation of that iron has to be +3. Okay, so that each potassium is +1, iron is +3. That gives me my +6. Each cyanide is -1. That gives me a -6. Okay. Now, unlike my naming with my complex cation, the name of the metal that's part of my complex ion changes when my complex ion is an anion. Okay, so I want to put up the chart really quick so that you can just see what some of these name changes are. So this particular table it's only used when we're naming a metal that's part of a complex anion. When we're naming a metal that's part of a complex cation, like you saw already, we're not going to use any of these name changes. But in the example we're doing now, our complex ion has a negative charge overall. And that means that we have a metal that's part of an anionic complex. All right. So once you decide that you're working with a complex anion, now you're going to find the metal that you're working with on the table, and you're going to use its specific anion name when you're naming the compound. Okay, so iron is called ferrate. So now instead of saying that we have hexacyano iron 3, we're going to say we have hexacyano ferrate 3. Okay. And this is the name of our complex anion. Okay. Now, because we're working with a compound that has a simple cation and a complex anion, remember I said the beginning part of our name is just going to be our potassium. So the full name of this compound is going to be potassium hexacyanoferrate 3. Sorry, that's a big space between that. There, that looks a little better. Potassium hexacyanoferrate 3. Okay. And again, the only time you're going to do this name change is when your complex ion is an anion, and you see the brackets are at the end of that compound. That's kind of how you know. All right. The last example that I want to do is going to show just how you go about naming when you have some ethylene diamine as part of your compound, so we can like see it in action. Okay, so when you see a compound like this, again, the first thing that you would start doing is looking at this and recognizing the fact that your brackets are at the beginning of your formula. So what you're working with here is going to be a complex cation. All right. And then you have one type of ligand present, and that ligand is going to be ethylene diamine. Notice how when you write ethylene diamine, there's only one M, but when you're using amine on its own, when it's just NH3, there are two M's. It's a weird change, but it's worth knowing. So this is the name of our ligand, and we have three of them. So it's going to be tris. Tris-ethylene diamine. Okay, now we have to name our metal. So before we can name our metal, we need to find its oxidation state. The other thing that you have to know about the ligands, aside from whether they're monodentate or bidentate or hexadentate, you have to know which ligands are neutral and which ligands are charged, okay? Because when you're doing the oxidation states, like we saw in the earlier examples with the ammonia and the water, like when you know that your ligand is neutral, that information helps you find the oxidation state. So be aware of that. We can tell, well, we know that the bromide is going to have a -1 charge, and there are 4 of them, so we can write that down. That total negative contribution is going to be -4 then. Ethylene diamine is neutral, so it's going to have an overall oxidation of 0 when you add everything up. And what that means is that your platinum is going to have an oxidation of +4 to counteract the -4 that's here. Okay. Because it's a complex cation, we do not have to change the name of the metal. So we're just going to say it's tris ethylene diamine platinum 4. And this names our complex cation part. And then we're going to finish out the name of the compound by naming our simple anion. So we'll have space and then bromide. Okay, so this is going to be our full name. Tris ethylene diamine, platinum 4, bromide. All right. It's not too terrible. Just make sure that you are working through the practice examples, like with the steps in front of you, with your charts in front of you, so that you're like looking at the stuff constantly. And if you practice this, I don't know, 6 or 7 times, it's going to start clicking, and it's not going to be that tough.